Today we'll be covering NVH topics. NVH stands for noise, vibration, and harshness. This presentation will go over some fundamentals of NVH, some of the factors affecting the NVH. We will talk about numerical optimizations, that is, the tools that are used to optimize the NVH behavior and characteristics of parts, systems, or components. We will talk about examples. We will also talk about standard experimental optimization and some advanced tools that are used for optimal design modifications. We will show some examples. And we will talk in general about NVH improvements and what people can do as far as design and simulation and testing to improve the NVH characteristics and behavior. We will also conclude with a summary. Fundamentals of NVH. Basically, it goes back to the fundamental of NVH, which is the free vibration and the lump mass model. Most of us who attended engineering school or some kind of engineering or industrial type school went over some mathematical formulation with respect to NVH. This slide here shows a simple mass and spring system. The spring stiffness is represented by the factor K. The mass is represented by the block. This system has an inherent natural frequency, which is basically the response of the system to a certain induced motion. So basically, it's a single degree of freedom model. That means it moves only in one direction, and that is the direction of the input or the energy that's being input. It responds with a natural frequency, which is basically the perpetual motion of this particular system. All systems have an inherent natural frequency. That is, metal, wood, plastic, any system that exists has some kind of natural frequency. If the system vibrates at the natural frequencies, the amplitudes are usually very large. So in NVH or any type of vibration reduction design, the engineer or the designer should devise ways to excite a certain structure or to make sure that the excitations of certain structures are done away from that natural frequency. Now, there are ways of extracting these natural frequencies, and we will talk about that specifically in other slides. Again, the first one that I showed was a simple mass spring system without any damping. However, there are damping factors that are induced into the system, and that adds another factor to reduce the vibration. So basically, a typical sinusoidal type vibration, which actually represents this simple mass spring system, will decay with time. And that's essentially what the damping does. Basically, it means to absorb the energy over time. The damping concept itself is very important because it affects the overall structural system. Again, depending on the level of that damping, the actual vibration level, which in this instance is the force vibration, is depicted in this amplitude angular velocity type plot. Essentially, it shows that with zero damping, you have a very large amplitude, which goes to infinity. As you increase the damping, that amplitude goes to zero. Basically, it's very important to have a damping factor and to configure that damping factor so you can reduce the energy or the excitational response of the system to a certain exciting energy. Natural frequency system or characteristic can be extracted by doing a simple finite element analysis model. Essentially, the structure, which is represented here by a supported plate, is depicted in a finite element model where the surface of that structure is subdivided into elemental parts and represented mathematically within a certain code with the proper stiffness information. Then the input parameters would represent what a free vibration system would do and what those amplitudes would be. There are ways, mathematical ways in every code or simulation code that exists today where you can get natural frequencies of the system by doing simple equations. And the pictures here that are multicolored represent the different modal frequencies that are basically the shapes associated with that particular frequency level. So each frequency makes that system vibrate or move in a certain way or form, and that form is basically represented by mode. So mode 1 represents the deformation of the system at that 153 Hertz frequency. Mode 2 is deformation of the system at 383 Hertz and so forth. Typically, the deformation and the amplitudes that are generated during deformation are basically what diminish, as you increase in the frequency level, and that is in the harmonics, what's called harmonics, which is a multiple of the first frequency. So the amplitude is highest at the first frequency, and then it reduces gradually as you go up in the frequency level at a certain harmonic. The sound wave itself is a pressure wave. It's a disturbance in the molecule in the air that it propagates through. That air is referred to as an elastic medium, and it propagates at a certain speed. There are two fundamental sound generating mechanisms. Those are the vibration of solid elastic bodies in contact with the fluid medium that represents like the air and then the speech, for example, and the vibrations that, for example, if I'm talking right now and my voice will impinge on the table that's in front of me, the actual acoustical wave propagates through that elastic body. And however, so there's the mechanism here is that the acoustic wave is in contact with the fluid medium, which is the air, and the air transmits that acoustic frequency through the solid body. And then there are the pressure fluctuations generated by turbulence or unsteady flow. So that is, if you have, for example, a car system or a fan, and you're generating air, and that air itself represents some turbulence, and it represents some unsteadiness, and then it creates vibrations. The sound wave, while the sound pressure level is a measurement of the actual energy that represents sound, and that is predominantly referred to as SPL. So it can correspond to a certain frequency, a frequency band, or the sum of different frequency components. The human ear can hear audio frequencies in the range from 20 hertz to 18 kilohertz. And these frequencies can be split up into bands. These bands are predominantly referred to as octave bands. An octave band is nothing but a band that represents like a center frequency and represents an upper and lower range. For instance, for an octave band, it's represented by a ratio of the upper range frequency to the lower range frequency with 2 to the power n being a number that can vary from 1 to infinity and equal 1 for an octave band. So that means the octave band represents a center frequency and an upper and a lower frequency band. It's just an easier way to refer to frequencies in the time domain. And there is another measure, one mostly used measure for acoustical energy, which is the sound intensity and the sound power. And there are ways of measuring the actual sound intensity using the sound intensity probe, sound power as well. There are also some ways of extracting that information from codes by doing mathematical integrations and so forth. Factors affecting NVH. There are several factors that affect the NVH behavior. Those are or can be mechanical or acoustical. There's the stiffness of the actual system or component, the damping, as I mentioned before, the mass of the system, and then the absorption or reflection of the subsystems, such as absorbers or barriers within the system. There are definitely some mechanical excitations from engines, motors, cams, and so forth. And the easiest way to illustrate that is to think about an automotive engine. We have different components that are interlinked and that are cyclical and generating vibrations. In an engine system, the mechanical excitations, for example, are related to engine orders. Those are orders or multiple of the actual engine running speeds from vibration isolation systems such as engine covers and so forth. Those are basically represent the sources. So an engine itself firing is a source of mechanical excitation because it's vibrating, it's generating sound waves, and those sound waves are propagating through the elastic medium, which is basically the body or the surroundings of that engine, basically that creating the vibration on the surface of these components. However, some of that vibration gets transmitted to other components because they're attached. So basically here, if you have a flexible coupling, for example, an isolator, or grommets, the actual elastic body waves are transmitted through those connecting points. The acoustical excitation can also happen due to the fluctuation of the pulsation of the air that's inside an air intake manifold, for example. So it is the pressure impulse from the engine, from that combustion that's going on and the firing and so forth, and it is related to the actual speeds. Here we're trying to illustrate the different means or mediums, for acoustical excitations And we're trying to focus on automotive engines, but this is very true in any type of system where there is fluid medium going through, or like, for example, on an agricultural engine, for example, or an air conditioning system. There are certainly acoustical excitations generated by the air that's flowing into a duct or so forth. So this is not limited to an automotive engine. It's just easier to illustrate these concepts using those examples. There are certainly very high frequency excitations as well that are generated, like, for example, with power tools, like a circular saw. The blade itself that rotates 30,000 RPM or so forth generates quite a bit of turbulent airflow, and therefore noises that are associated with like whistling type noises. These are referred to as higher order acoustic resonances. When you're operating machinery at a very high speed, typically the excitations occur with higher order frequencies. The stiffness of the component has an effect on the actual NVH characteristic. So this, in the durability study, for example, is very important. Stiffness itself, as if increased, will prevent high dynamic loads at critical point designs, at the ribs, at the curvature, shapes, and thickness. The acoustical radiation is affected also by the stiffness, because the more rigid the component or the system is, the less acoustical energy is going to be radiated due to the flexibility of the surface where it's emanating from. Essentially, what we're saying is increasing the stiffness. By increasing the stiffness, we can shift the structural modes into higher frequencies and therefore achieve lower amplitudes, lower deformation amplitudes or modal shapes, deforming at a much lower level. I talked about damping in a few slides before this one, and damping is critical because we can control the response of the resonant frequencies. So it is typically used to reduce the excessive vibration level at the critical points, reduce noise level to the radiation from structural modes, and it is used as energy absorption because the damping medium itself can absorb energy. Typically here, we're talking about materials and plastic materials, specifically nylon. The damping characteristics of nylon are better than metal, and that is a fact. You can actually take a piece of metal and take its equivalent into a nylon just by tapping on that surface of that component. Both materials, you'll see the difference in sound level emanating from either component. The mass itself affects the NVH characteristics, in particular to sound transmission loss. What I mean by sound transmission loss is the ability of a material to reduce the sound energy transmitted through that material. The higher the mass of the barrier, referring to sound transmission loss here, so we're referring to barrier systems. So the higher the mass of the barrier, the lower is the noise transmission. So it's strictly related to the thickness of the mass. So doubling the thickness of a panel, for example, reduces noise transmission by 6 decibels, which is significant in acoustic board. There are 3 distinct regions where we can identify certain designs with. So, for example, there's the stiffness and resonance controlled region, which is associated with lower frequency ranges. And then the mass controlled region, which is basically predominantly controlled by the mass, and it's a medium frequency range. And then the coincident region, where it is the higher frequency range. Typically, like I can refer to like barrier systems, those barriers that are used on highway, where they are used to reduce the noise level from the road near like a neighborhood or so. I want to talk about some numerical optimization tools, and in particular some computer-aided engineering tools. So we have a structural analysis where we can actually get the model, do model analysis, get the natural frequencies, and then we can take that into a frequency response analysis and basically extract the response of the structure based on the frequency signature. We can also do some acoustic analysis by looking at cavity response analysis, that is the source or the wave inside a box, for example. We can look at uncoupled structural acoustic analysis or coupled structural acoustic analysis, meaning that whether there is compliance between the medium, that's the exciting medium, and the surface of the structure or not. So we can simulate it as uncoupled or coupled, and then we can do the optimization using the optimization tools within the code. For structural dynamic analysis, it starts with the material data and a finite element model and some boundary conditions. We extract the normal mode for the analysis. We introduce the excitations and damping. We have to know what the damping is. And then based on that, we can get what we call the motor position and the structural frequency response. From that, we extract the displacements, velocities, and acceleration, as well as stress. It's a very powerful technique used. In the numerical acoustical optimization, we take the structural frequency response that we did in the beginning, And then from that we extract the velocity boundary conditions, because that part is moving at certain frequencies, so we can extract out the velocity boundary conditions. We can create what we call field point meshes, which are representation of like microphone locations in space that surround a certain structure. The actual structure is represented by a boundary element model, which is a skin model that represents the velocities at that surface. And from that, we can do an indirect boundary element analysis. I'm referring to boundary element analysis as the analysis used for acoustical studies, and it's called boundary because we're looking at the surface factors. And then the indirect means that we can do it for openings, so you can have openings within the structure and you can still do the analysis. So you can have holes and do the analysis. From that you can get multiple parameters such as radiation efficiency, sound intensity, sound pressure level, sound power, and so forth. It's also a very powerful technique. To do some numerical acoustical optimizations, we can look at the peak acoustical response. We can go back and identify these key structural modes. So basically we can do that sweep and look at the different contributions from the different factors and whether it's elastic or inelastic. And we can look at, for example, the orders, like in case of an engine, we can look at the orders that this key structural mode is occurring at. And then we can implement some modifications to the structure so that we can control these modes. And we can do all of that using optimization techniques in this code. Some of these examples, and I said that we can do an indirect study where we can look at openings which are represented by the entrances of these different manifolds. We can look at the acoustical response peaks at different frequencies, and based on that we can go back and maybe introduce some design modifications. In this case here we noticed that there was an excessive motion right at the center of that manifold, so we went back to the design and we connected top to the bottom surface using stanchions. In the design we went back and redid the analysis, and we saw that this affected the analysis. We were able to reduce the actual vibration level. Another example is valve cover, vibration isolation, looking at different techniques to secure that one and get the reduction in the vibration. By doing the proper adjust to the molding method, we were able to reduce the actual vibration level significantly, as shown here in this graph. Bracket, we were converting the metal to plastic bracket. We had to basically design it so that the target first mode was greater than 50 hertz. We had to do it at certain temperature levels and meet certain target weight reductions. We have a tool that actually goes back and based on parameters that we input as far as the thickness and where we want it to optimize structure, it can go back and tell us topologically what areas need most stiffness, so therefore remove material from it and just put the material where it's needed. And this is another powerful technique. Based on that we can extract the natural frequencies of the system. Again, we can do the analysis so that we can get the actual improvements as well as the actual surface movement. An oil pan, this is very similar to the previous one where we were looking at different modes. We were looking at reducing, the amplitudes at these modes by removing the structure. Experimental optimization and experimental tools. I mentioned those in the beginning. We have several on location as well as overseas. We have what we call an electronic speckled pattern interferometer. And basically what it does, it enables us to lay a grid over the structure and extract the surface depiction of that structure readily. So basically we can kind of like take an image, assess what the vibration level is or the movement, right at the surface. So we can excite the structure, and based on that we can get a representation of that structure, and it moves very quick. We have an array of different recorded sound intensity probes to actually doing sound intensity, which is done typically perpendicular to the actual grid that's laid out in this picture here on an engine. Basically, the sound intensity is used when you have like a noisy environment, therefore it's easier to control the environment and to extract data that is meaningful. Another twist testing tool is basically to look at the acoustical parameters by creating a structure that you can rotate 360 degrees around a source or a noise source, such as the intake manifold here, and then we can extract the parameters from the sound pressure level or sound intensity by rotating that structure 360 degrees at a 5-degree increment or more. laser vibrometry, where we can actually extract the actual movement at the surface based on the velocity Doppler shift. There is a laser that gets pointed on the structure and then gets reflected back, and it's read by the machine. We do that at different points on the structure that are basically represented by grid, and then we can get the information readily on the screen. Again, sound intensity and sound power measurements are done according to standards. I mentioned those before, so I don't need to get into it again. The whole process, in terms of acoustical optimization, is to get a sound recording or to digitize the sound, to manipulate it, to look at different recordings from other places, do some comparative studies, and then to do some further modal analysis, the speckle interferometry. And then we can look at the results, employ the correct modeling techniques to reduce part variations that are adequate to reduce the vibration level. And there are several prime noise control methods that are mentioned. One of them, which is dampening, mentioned. Another one, which is barrier. Another one is absorption. So you have like absorbent structures or foams that are laid under some kind of component to reduce the vibration level. I mentioned before that the sound transmission loss is a function of the mass and some major and minor parameters. The major parameters are related to mass, and the minor parameters are related to actual parameters, like such as modulus of elasticity, the angle of the sound impinging, the loss factor, which is stored energy, and so forth. We also have means to predict what the sound transmission loss level is based on standard formulations. So we have the tool to do that. Some of these examples, we were looking at an intake manifold again. We extracted the sound pressure level or the sound intensity at different locations for that engine. However, this is the original design on the left and then the right design on the right. And it shows clearly that the map of that sound intensity is much reduced than the left figure. So we ended up with an optimal design where we actually ripped the structure across, as shown. This slide shows the improvement from the aluminum, which is the benchmark for the study. Another one is looking at an air intake manifold and air rush through a throttle body, and then it gets into the plenum and then goes through the flange and so forth. We were looking at a turbulence situation. We looked at the actual waterfall or energy that's propagating, per engine orders. So the red area shows when most of that energy occur. The sound intensity measurement itself allows us, to depict exactly where the sound is emanating from. So basically, looking at the sound power map and looking at an overall 0.5 to 10 kilohertz, we can depict exactly what's influencing the surface. Again, depending on that turbulence, we can see what the actual original design, is in comparison to the new design, in case we made some modifications to that design. In this case here, we were using a dynamic absorber. So basically the problem was the vertical mode of the manifold at 225 Hertz was the cause of the major noise concern. The proposed solution was to design an acoustic mass dampers, dynamic absorbers that would reduce the vibration level by 225 and thereby the noise. Essentially, when you reduce the vibration level, you are reducing the noise. Basically here we went through the process of designing that damper and several configurations and comparing all of these. Lastly, I'm going to talk about NVH improvement. What can you do to improve NVH or the vibration level? For vibration control, I certainly mentioned design modifications, mass dampers, dynamic absorbers, vibration isolation, damping materials. All of these affect the vibration level and therefore enables one to control the vibrations. The noise, again, by design modifications, using screens, barriers, absorbers, enclosures, mufflers, resonators. Again, barriers were subsystems, so there are several ways of taking care of that vibration. General design guidelines for radiating surfaces. The radiating surface should be reduced to as small as possible, a shell or membrane surface. If you have to stick with a certain size, then you should probably increase the stiffness by ribbing the structure or ribbing that surface, curving the surface and so forth. A cross section that is like oval, maybe not as good as making it round. Like prefer circular cross sections to streamline the airflow a little bit better in case there's a fluid medium there. Like a big cross section divided into smaller round cross sections, for example. for where there is excessive movement, maybe use some connecting features to reduce that movement between two surfaces. And in summary, in the low frequency regime, you can control vibrations by looking at vibration isolation, mass dampers, resonators, or design modifications to prevent the structural and acoustical resonances. In the high frequency regime, certainly absorbers, barriers, and enclosures, the mass is very critical in that area. And I would say medium to high frequency. The NVH characteristics of plastic components can be vastly improved by proper component and system design. I can't emphasize this one, that much, as much as saying to look at flexibility in the design. If you wanted to improve a plastic design, certainly call onto BASF. We have a lot of expertise in that area, and we have a lot of expertise in doing actual simulations to help you improve the design.